So, welcome everyone to today's installment of our speaker series, Frontiers in Monitoring Supported Decision Making. It's my very great pleasure to announce today's speakers, which are Professor Jannie Nielsen and Kostas Papakonstantinou. They will talk about artificial intelligence-driven optimization of monitoring and maintenance policies. And as last time, we have presentations that will be close to 1 hour by the two of speakers. And then we have around 30 minutes of joint discussion. If you have questions or comments, please submit them in the Q&A panel. This you can do already during the talks. And then we will try to pick up as many of these questions and comments in the discussion. The first speaker today is Jannie Nielsen, and she's an associate professor at the University of Aalborg in Denmark. She has extensive experience with the reliability and risk assessment of structures in general and wind turbines in particular. And a special focus of her work is on risk and reliability-based planning and optimization of inspection, monitoring, and asset management. And I'm very happy that she is going to present today and discuss with us afterwards.
Okay, so I believe that you should be able to see my screen now.
Perfect.
Perfect. Okay, so as Daniel said, so this the topic for this presentation is AI-driven optimization of monitoring and maintenance policies. And so I will give part one of this, and Kostas would go on with some additional aspects in this relation. So basically, the research question that we are addressing is, so how can we optimally plan monitoring, inspection, and maintenance for structural system? Well, taking into account basically all relevant information. Well, so as many of you know, well, we have this theoretical basis in the Bayesian decision theory, where what we basically do is to minimize the expected cost. So generally, what we'll see is that if we increase the maintenance efforts, we have larger cost to maintenance, but also less cost to expected failures. So we want to find this optimal where we have the lowest cost. So the contributions are made up of could be cost to monitoring, to inspections, to repairs, and to failures. Of course, this figure is just in one dimension with just maintenance effort on the first axis. In reality, we would have many different decision options, so it would be like a multidimensional problem, so making it much more complicated. So basically here we are looking at integrity management of structures. So we wish to assess that the safety or reliability is sufficiently, or is acceptable looking over time. But of course, that's not enough to just make the assessment. We also need the actions to ensure that the sufficient reliability is actually achieved. And we want to do this at the lowest cost possible. So here we are looking at different degradation mechanisms. So we basically want to avoid that we are having these failures. So there are different types of information that we could use for this assessment. There's of course the design model, so that could in relation to fatigue be an SN model. We could also have some deterioration models not used in the design, but that can be used for assessments, for example, fracture mechanics models. We could have inspections where we have some data monitoring, both structural health monitoring, where we actually detect damages, but it could also be environmental parameters or the load monitoring. And we could also have information on maintenance that is performed. So we basically want to use all of this and then like put it into this decision optimization. So we need to satisfy the constraints given by higher authorities. Then we need to minimize or maximize of the objective function depending on whether it's like defined as expected cost or utility. And well, the things that we can adjust here are these decisions that we can make. So we can make decisions on collecting more information. So this could be online monitoring, where it can be different options for methods and location. It can be inspections, where it's also different location, point in time methods. And then there are these different actions that we can do to actually improve the reliability. So basically what we want to do here is to know how do we play this game of integrity management in optimal way. So the vision that you could have here is to, well, extract all useful information from all the data you have, consider all relevant available knowledge to make these optimal decisions. So, well, can artificial intelligence do this for us? So looking at artificial intelligence, well, we study intelligent agents. So it's something that like perceives the environment and takes actions that maximize its chances of successfully achieving its goals. So these algorithms can learn directly through interaction with the game and can improve over time with the experience. So for example, they have shown that they are really good at actually playing games. For example, these arcade games taking input, so only visual input or information on the color of the pixels, and then actually learning how to play the game just based on that. So like a human. And also they have now beat, or some years ago now, beat humans in playing chess. So they are quite good at playing games. So, well, playing a computer game versus playing this integrity management game, is that then the same deal, you could ask? Well, when playing a computer game, you might get this game over screen, and you'll need to insert a coin to continue. Well, if you're playing the integrity management game, then it's a bit more unfortunate to get this game over screen. The coins that you need to insert to continue is a bit bigger. Here it's a wind turbine that has collapsed, but it could also be a structure where there are actually human lives that are compromised. So, well, obviously we cannot just learn from the data by actually playing the game. So what can we do instead? So what we could do is to learn from data from past experience. So we already discussed the types of data that could be available for the assessment. But we should also, well, realize that there are some limitations here, because these data, they represent what's come out of the existing monitoring and maintenance strategies. So we do not necessarily have any data on what happens if we get outside this strategy. Might have no or few failures. So if we just use the data and let an algorithm learn from that, then it wouldn't know what happens in these more extreme cases. So I think, well, we can say that we need to combine models and data. So, and also, well, we need to be able to document the reliability and understand the model driving the decisions. So what we basically need to do here is that we need this probabilistic model, this kind of integrity management game that we can train our algorithms on for optimal decision making. So we have identified some challenges in relation to these parts. So one is related to the upper part and concerns this, well, this lack of reliable models or data to actually make this probabilistic model. Yeah. The others are related to this optimal decision making. So it's there's high computational complexity, and we need also transparency in this reliability assessment and the decision maker. And well, we would also like to, well, directly use online structured health monitoring data in this decision optimization. So first I will address this first point regarding the models. So let's have an example here with the wind turbine blades. Here you have can observe cracks, and well, if you have had a steel structure with the cracks in the welds, well, you could probably get the idea to do as have been done before. So take the SN model that was used in design and calibrate a fracture mechanics model based on this, and then you have a probabilistic model. But this is a much more complex structure with an anisotropic material. It's a bit more complicated. Well, what you could do instead is to utilize that you actually have databases with the inspection of defects. So what you could aim of is to build a model. So if you have some observations, different points in time, and you also have information of relevant input parameters, you could try to learn a model based on this. So the data that could be relevant here is observations or information on the state, both initially, so after installation, also after maintenance. It's this inspection data, so observations of the state in various points in time, various locations. And it's also, for example, the scatter data with the environmental loading parameters. So it's maybe not so easy. At least you should acknowledge that there will be variability in this data. So you will have many different wind turbine models, blade types, different environments, different inspection types, and many different defect types. So you need to, at least in the model, account for that variability. But then maybe bigger problems is that what you often see is that there may be limited data with more observations of the same defect because they get repaired after findings. And well, you might also have the situation that in the database, well, you have no information on performed maintenance, and these other information that you need also in the SCADA data might not be in the same database, may not even be available to the same stakeholders. So that's a huge practical challenge in this relation. But if you then, well, actually manage to get this data that is needed, well, you could approach this problem of learning from data in different ways. One approach could be to use a black box model, for example, a deep neural network model, and learn from that. I think at least when at some point we would like to have something that is like that you can actually understand and use for reliability assessment and include uncertainties. So an option is also to use like a Bayesian network model. So here there are learning algorithms that can learn probability tables in discrete Bayesian networks. Here you will get the problem that even if you have large databases, you will also have like large variation of the data sets. So you probably end up with the like still quite sparse data and end up with the like empty holes in this probability table, or in not really something that is like a uniform or smooth in the way it behaves. So yeah, I believe that the solution that we should go for is to have a model with parameters and then learn these parameters. So it could be a quite flexible model with many like degrees of freedom, but still a model based on parameters. So basically, the way we could approach this is to like use all these past data sets with observation relevant input, combine this with some qualitative knowledge to have this a data-driven model where you utilize this past data. Then if you want to use it for decision making for a specific problem, there could be some input parameters where you then know what are these relevant ranges or values, and then having this specific model, but also including enough uncertainty so you can allow the model to adapt to the specific case if this model is still quite uncertain. Yeah, so this was some notes regarding this first point. So then going to this parts in relation to the decision making. Well, so as I mentioned, well, looking at this decision-making problem, you will have many decisions distributed in time related to monitoring, when, how to inspect, when, how to repair. And well, to solve a decision problem like this exact, well, basically you should consider the entire future when making decisions, and also include all past observations. So this fast becomes intractable, especially if you are considering that you might have a structural system with many components. So the way this can be tackled is to use some decision policies. So there are different options. Can be heuristic options, be based on POMDP or based on DRL. So I will consider this first option here, and then Kostas will address these other approaches in his presentation. So basically, the starting point for this approach that I use for these heuristics are this discrete Bayesian network formulation, where all models are specified as discrete conditional probability distribution. So a deterioration model or degradation model, repair model, inspection model, and monitoring model. So a heuristic decision rule that considers structural health monitoring, well, a very simple approach could be to make the inspection directly based on the latest monitoring outcome. And this outcome could be, for example, some mean value over a period of time. And then, well, with this approach, then a Bayesian network can be used to actually find these costs for a different for a given strategy directly, because, well, this so the monitoring observation will depend on the damage, and the inspection decision will then be defined based on this one, and the inspection outcome will then depend on also on the damage state and the inspection decision, and based on this inspection outcome, we will make a decision on what kind of repair to make. So in this way, we can calculate these expected costs. So this is like a quite simple approach, and maybe a bit on the edge of what we would call AI. So a more advanced approach here is to base the inspection decision based on a threshold for the failure probability. So here it's you can find the expected cost using simulations, and then within this simulation applying this Bayesian network for updating. So every time you get a monitoring observation and every time you then do an inspection and get information, you update the network to always have an update assessment of the failure probability, and then you use this for decision making. So just to show how it works, I have here like 3 examples with these 2 that I just mentioned, and then also a strategy without structural health monitoring, so just with the equidistant inspections. So looking at a simulation of the damage over time, you would have inspections, and here you can see that if an inspection finds an outcome about this threshold, a repair is made. Going to this simple structural health monitoring strategy, you would still have this simulation of damage, but would then also have these structural health monitoring observations. And when they are about this threshold, an inspection is made, and if findings are then, or if observations here are found about this threshold, then a repair is made. And going for this advanced strategy, you track this probability of failure over time. So each time you get an observation, you update this, and when you exceed the threshold, then an inspection is made, and if findings are made about the threshold, then a repair is made. So this is basically how it works. So I made a case study this together with some researchers in the area of structural health monitoring who had made a previous project where they did this demonstration on operating a turbine of this of a blade structural health monitoring system with an actuator that made vibrations, and then they had these accelerometers where they measured the response. And then they introduced this artificial crack of first 15 centimeters, then 30, then 45 centimeters, and made like this test campaign based on this. So if you look at this, so this shows the damage index that is found based on some Manhalobis distance, and then the samples taken here. What they did initially was to take this first part as like training data, and then using an unsupervised learning approach to then find what is then the detection rate and false alarm rate in this test data. And they did this for different allowed false alarm rates corresponding to different thresholds, and could get curves like this. What we then did in order to make a monitoring model here was to use this curve then to take it as supervised learning. So associating these different crack sizes here with some damage size, and finding the probability of exceeding different of these thresholds out of these curves. So we had some different sensor configurations, where this was the one we showed for before. And then we also had some that were more reliable, where you can see that this one has a really high correct detection rate. So coming out of, we then use this approach as I showed before, so with equidistant inspections and these different structural health monitoring strategies. So basically varying these input parameters or these decision options, so inspection interval and repair threshold, we could see how this would affect the expected lifetime cost. And for each of these cases, then identify the optimal. And we did this also for the other sensor configurations. So looking at the results, what we could see was that these advanced strategy always perform better than simple, as expected. But also that the most reliable structural health monitoring configuration actually performed the worst here. So this can sound a bit surprising, and well, so here these thresholds would show based on these false alarm probabilities that they usually used in this unsupervised learning approach. And they, well, looking at this very reliable sensor configuration, the highest threshold corresponding to this full line. And as you can see, well, this is not really high enough to actually distinguish these different defect sizes, and it's not feasible to initiate inspections based on cracks that are too small, so small that they shouldn't be repaired yet, if that's optimal. So that's definitely the reason for this. So optimally, you should have, or this one would give the basis for better decisions if you were using them optimally. So this was based on a test, but if you were to install a monitoring system on another wind turbine or fleet of the wind turbine, then, well, how would you know how a real crack would affect this damage index? Well, you wouldn't really know that before installing it and before getting some data. So there's definitely a need for including an uncertainty in this. So you don't really know if it looks like something like this, where we have a large variation in the points, and then you get some small increase due to the damage, or if it is like this, where you have it's much more distinguished, these different damage sizes. So I made another study here where we're looking at how can we include this in the model, and this can be done like by including a dependency parameter, so that it also affects these observations. So basically, we will assume a relation here of how this expected outcome of this monitoring observation is affected by damage size and this parameter. So I had a model like this, where we, with a special case here was this linear model, but then it could also be this more exponential behavior. So basically, assuming that we had these, the direct monitoring signal was this continuous time series with the high frequency, then based on this, we would find a damage index that could be derived, for example, based on outlier analysis. This could be once a day. But then for this decision making, we would then have this statistical value. So the sample mean once a month, so where we assume this a normal model. Then looked at these different cases. So both this equidistant inspection based on latest monitoring outcome, and inspection based on failure probability. Looking under these 2 or 3 cases, having uncorrelated observations as like the normal case, but also having correlated observations through this dependency parameter. And then the case where we had actually correlated observations, but in the model we did not account for that. So we assumed they were uncorrelated when we were making decisions. So what we end up with here is that if we are in this case where we assume uncorrelated uncorrelated observations when they are in fact correlated, we could end up with much larger amounts of failures compared to this uncorrelated case, and also therefore much larger cost. Whereas if we had that we actually did have a model where we accounted for the correlation, if we had the simple strategy, it wasn't performing much better. But with this advanced strategy where we had this probability of failure that we updated each time we had an information, then it was performing more similar to this case. So all this was case dependent, regardless of this value of this the shape of this relation. Also made other studies into how different parameters affected it, and it was always like the same picture here. So in some of these cases, we would actually end up with a negative value of monitoring, well, because decisions were not made in an optimal way, basically. So some concluding remarks. So if we do this AI-based integrity management of structures, we need a probabilistic model for this integrity management game. And we need parametric models, including all relevant uncertainties and allowing to adapt to the specific data. We need to install structural health monitoring systems, I believe, to get data on their performance, to actually know what will be the value. We can make assessments based on what we believe, but we do not really know before we actually install them and run them. And then the decision makers should always be able to understand decisions recommended by artificial intelligence. So we will have to make that trade-off between simplicity and optimality. So with this, I would thank you for your attention, and well, I'll be happy to answer questions after the talks.
Thank you very much. Maybe here just to remind everyone to also send us to note their questions in the Q&A. And please, if possible, maybe also refer to the speaker when you fill this out. Now it would be my pleasure to present the second speaker for today, who is Professor Kostas Papakonstantinou, and I also have the pleasure to know him since our years in the National Technical University of Athens, where he obtained his 5-year diploma in civil engineering, as well as his Master of Science, and then he proceeded to obtain his master's and PhD degrees at the University of California at Irvine. He is currently at Penn State, where he was an associate research scientist at the department, or prior to joining Penn State, he was a research scientist at the Department of Civil Engineering and Engineering Mechanics at Columbia University. And his work, part of which he will be discussing today, focuses on the probabilistic analysis and stochastic mechanics, decision-making under uncertainty, and machine learning for a solution of inverse problems. He has received a number of awards as part of this research work in these domains, including an NSF Career Award exactly on the problem of decision support. And so I give him the floor to elaborate on this.
Thank you, Eleni. Thank you, Daniel, for organizing the event and for inviting us. Thank you, Daniel, for the very interesting talk, and our second talk in this series with the same topic. Let me try to share my screen here. Okay, so what do you see the right thing?
Looks good. Yeah.
Okay, so this is along the same thing we have been discussing, AI-driven optimization of monitoring and maintenance policies. I'm Kostas Papakonstantinou, and this is a joint work with Karolinas Andriotis mainly. He's currently an assistant professor at TU Delft, and some former parts of this work with my late former advisor Masanobu Shinizuka. So since we will be talking about reinforcement learning, and you can follow here the talk, right? Just a little bit of introduction to place it into the general AI content, right? So reinforcement learning has a big history in psychology about the reward system of how people are learning, humans. And it also has ties to computer science through machine learning, engineering, and mathematics through operational research and optimal control. And if we see this as the sphere of artificial intelligence, right? Machine learning is a part of it, and it has three main components, right? Supervised learning, unsupervised learning, and reinforcement learning. And of course, if we add neural networks to all of this, right? We have their deep version. So we're dealing with computational models, right, in our investigations. And a computational model is a mapping, right, from the input. And if we have a probabilistic model, we have we may have a joint PDF, and we do uncertainty propagation, and we get the output for this. So how about if we do this time a direct mapping from input to actions, right, directly to find the actions to perform. So this is what reinforcement learning is actually doing, right, is learning what to do. How to map situations to actions, right? We have an agent, we take an action that goes through the environment, right? And then we get the reward and the state through that environment. So there are many problems that this can be applied, right? In our case here, what we're discussing is the lifecycle management policies for large-scale engineering systems, right? So the problem characteristics is that we have long-term objectives. We have various forms of uncertainties, right? Real-time and noisy data, incomplete information, dynamic transitions in time, and probabilistic actions. And this is a sequential decision-making problem, right? So we're trying to find the optimal policy pi star And we're trying at each step to optimize these rewards, right? Can be maintenance, can be inspection, can be rewards that have to do with certain risks, economic, societal, environmental risks. The problem is that the environments are dynamic, right? We're trying to make decisions for long time periods, so things change over time. So we need to incorporate stochastic models and real-time data, and certain real-time data to ideally be able to have real-time optimal decisions. So a framework for this is the dynamic programming arsenal of methods, right? Which they're also leading to closed loop stochastic control. Closed loop meaning that we have also knowledge about future outcomes. So if we see this equation here, which is the Markov decision process equation, or else the Bellman equation, we have this value function for every state S. This is the one we're trying to maximize. And we're trying at each step to find the maximum action. So A here is an action. These are the immediate rewards we're taking for performing this action, and of course also costs. This is gamma as a discount factor, and we have also all the possible future rewards for going on to a new state at time t+1. So this here is the probability given the state and the action, right? What is the probability that we end up in a new state? So that's the difficult part. This part is usually easy because it has to do with one step ahead policies, right? But the difficult part is all these future rewards that we may collect in the future. And as already mentioned in the previous talk, right, going forward in time is infeasible for large systems because of the different policies we have. So dynamic programming, what it's doing is starting from a terminal node, right, and goes backward in time. And then at state n, we have to take one step ahead decision. This is just this part, it's easy, then we know what's optimal and we go back in time. So why is this problem challenging? The first part is one reason is the curse of dimensionality, right? So states and actions scale exponentially with components. So if we have, for example, just 10 states for this building, 12 states for this, discrete states for this bridge, and 6 states for this wind turbine, this small world here will have 10 to the 16 number of states, right? Which it's a huge number. It's more than the Milky Way galaxy stars. The other challenge is about the actions that we can take. So if we only consider repair or no repair for this small world here, we have 10 to the number of 5 possible actions. Another problem is the curse of history. So the policy space scales exponentially with a number of steps, right? So for this small world again, for just 4 steps, we have 10 to the 20 number of possible policies if we start from here. We also may have real-time noisy data, so we don't know the actual state of the system through the inspections, and we may also have model unavailability. So the system dynamics may be only accessible through a simulator, right? So by model in this case, we're meaning explicit mathematical formulations, right? So if we have this explicitly mathematically, right, this is what we call a model. If we call the model is unavailable, we can have a finite element model or a black box simulator. So we just take data from at different time steps. So why the partially observable Markov decision process and for this problem, right, that we're suggesting? First, they alleviate the curse of history because of dynamic programming, right? So dynamic programming have this inherent properties that can deal with the curse of history. We also have, in the case where we can solve this exactly or with certain bounds, we have optimality or near optimality guarantees with this method, meaning we know how far from the global optimal we may be. The POMDPs also support partial information due to observational uncertainties from data, as we will see. And now if we combine them with deep reinforcement learning, we can also alleviate the curse of dimensionality and model unavailability I mentioned before. So there is potential here to be able to tackle these challenges if we combine all this together. So what is a Markov decision process? Right, just in brief, is actually this control problem here. We have our different discrete states. Each one is connected with a certain reward, and we can control this transition at different time steps through certain actions, right? So we want to find what are the actions to take at the different time steps to optimize this reward at each time step t. So this is our optimal action, our optimal policy that we need to investigate. And there are two functions, two fundamental functions that are related to this, and we will use later. One is the so-called Q function, which is the expected total return for any state action pair, meaning we are in this state and we're taking this action. And if we act with a certain policy pi in the future, this is the expected reward we're expecting to see. And the value function now, V, is the same thing, but taking account all the actions. So based on the policy that we have determined. So just relying on the state S, right? We're taking the expected reward that acting based on the policy we expect to see in the future. So this is again based on, to find this optimal value function, right? We can use the Bellman equation and dynamic programming principles. So this is just a quick, an output of this. This is for a simple problem, just two components, 25 states overall for the system, and just 4 actions, right? Do nothing for both, replace one, replace the other, and replace both. And this is a mapping, right? This is what we're getting if we solve this. We get a mapping based on the state, MDPs, right? In MDPs, in Markov decision process, we assume we know the state of the system with certainty when we observe. So based on the state we're observing, right, we get for each time step of 30 years here horizon a certain action to take. And note here, right, in this problem with just 25 states and full observability, right, the non-stationarity of the policy. So the same actions are not optimal for the same state according to what time we're in our horizon. So the partial observable now MDPs, right, follow the same principles. We still have to optimize the policy and the rewards. We also have now inspection rewards. We can choose what inspections to take. And the value function and the Q function are still there, as we've mentioned them before, right? It's the same idea. The difference now is that we're never observed the discrete states of the system. That's why they're in gray, but we have some data, some proxy data to give us some information about them. Right. So the problem with this is that now we cannot rely on conditioning the policy pi on the discrete states. We have to condition the history of observations and actions, and which is quite big. Or alternatively, we can condition it on the probability we have, updated probability after we take a certain observation, or else belief we have about the state of the system. So through Bayesian updates, the classical Bayesian updates, we are doing this. The problem with this is that now we have, beliefs are continuous, right? We don't have this discrete states anymore, but we have a probability distribution over those, which is a continuous quantity. So we need to reformulate our Bellman equation, and we can do this. We can rewrite the Bellman equation now in terms of beliefs about the state of the system. And this is a more difficult problem, of course, to solve. The good news is that the optimal value function, the one we're trying to find, is piecewise linear and convex, right? So very quickly, the reason why it's convex is because if we're more certain about the states of our system, which are here at the edges, for example, right, we take better decisions and we act better, so we collect more reward. The reason why this is piecewise linear is that nearby belief points have the same optimal action to take. So if we are, so what we have to do to solve this POMDPs is to identify the regions of the belief space here where certain actions are optimal, and to identify these hyperplanes or so-called alpha vectors. And this is how it looks, for example, for 2 states. So there are, these are some papers who have worked on this, and they have details. I'll leave it here since this is also recorded for you if you want to go back and see them. But I'll just very quickly, so one example, right? So we have a port structure. We had here a finite element model, but we cannot use in this framework directly this finite element model. We have to map it to a transition. So this is our model, right? A transition matrices that goes from a state 1 to remains to state 1, or goes from state 1 to state 2, and so on. And altogether, in this case, we had 132 states. The same deal for the likelihood of the inspections, right? So if we are observing a stage 1, what's the probability that we, actually the system is in stage 1 and so on. So we also need, in this case, this matrices, this likelihood matrices of, being in a certain state which is unknown. What's the probability of observing something? And we can have different qualities here of inspection based on this. So I'll go directly to results. So here in this POMDP framework, right, what we have is this mapping. So if we have if we find these alpha vectors, we have here our beliefs for where the system lies, right? So we have here in this 4 condition states, 80% that, mainly is probably in state 1. The true state is 2, which we actually don't know. So for this case, for this belief, the algorithm says, okay, do not repair, do not inspect. A year goes by, we have a stochastic transition, and now the beliefs are updated, and we're closer to, of course, to there is some increased probability of being state 2. For this belief, right, we're recommended to go do a visual inspection. We're doing a visual inspection, and a transition also of 1 year is in effect, right? We're updating our beliefs about the component. And in this case, says go do a minor repair and a visual inspection. So we're also doing the inspection. We're back at this belief of more than 90% in true state in state 1, which is also the true state in this case. And we can also see a video of this here, right? So if we have this mapping based on actual data that we collect, and updating our posterior probabilities every time about the stage of the system, we have this mapping, and there's this game of, the beliefs are changing based on this belief. This is the optimal action to take, and we do that, right? So we see here a replacement action around 6 to 2 years, and as we'll see later, it's not predefined that this interval we have to replace, right? It depends on what beliefs we have for the system, right? So it took more than 100 steps, for example, to replace it again, and so on. These are all the available actions we have for this system. So this also here are the, we can use the so-called point-based solvers for this. We have upper and low bounds for optimality. It took around 3 hours to converge, and it converts to the global optimal solution. So another advantage of POMDPs, in a recent paper we saw is that they inherently possess the ability for sequential optimal inspection decisions, as we saw, right? They recommend what inspection action to take based on available options. So they can also be used for long-term inspection and structural health monitoring schemes. So in this paper, in this recent paper, which is in print and there's also in archive, right, we're also showing that we can write the belief-Bellman equation, the one we saw before, in terms of the net value of information. So meaning that inherently, if someone uses a POMDP policy, right, inherently at each step, we're also taking advantage, right, without actually doing anything about it, right, the value of information for our system. So under a POMDP policy, better or more information cannot increase the step or the life cycle cost, right? So information necessarily improves the decisions. So is this, isn't this always true? It's not. So in the same paper, we're showing for a 3-component system, following an optimal condition-based maintenance, if we reduce the noise from 5% to 0%, meaning, perfect observations, the value of information is negative, right? So the value of information also depends on the policy that we are following. So, and then with this, again, same 3-component system, we can also quantify the value of structural health monitoring based on different observation accuracies, the value of information between the no inspection and the different options we have, and so on for long-term schemes in terms of their output, in terms of the policy we're getting. So going now to reinforcement learning in order to be able to scale up to systems, right? There are different reinforcement learning algorithms and approaches. There are some that rely on the value function, that V we saw before, or the policy function, that pi we saw before. And there are also cases where they use both, all right? And they're called actor critic. And there are also cases, again, with we use a model or not, meaning we have just data coming into our algorithm. So as was mentioned before, this new interest in reinforcement learning started with these Atari games, right? Some of you have played those probably, and with this paper, right? So that was found in 2015, and it says human level control through deep reinforcement learning. So for some cases, right, just observing the raw pixels, right, the algorithms learn how to play these games at human level or above, and in some cases below human level. But but the main idea here is that this weren't program, right? Just based on what we see, they learn how to play the games on their own through deep reinforcement learning. So then after this, this has been applied to many different games. The Go game, chess, and also games like Alpha Star and StarCraft and Dota 2 and so on. So what's the main idea of this? It's actually very simple as an idea, right? Is that when we have immense state spaces, right, the Q, the value function, and the pi policy, right, are enormous. So what if we just parameterize them through some parameters theta, which are connected to our neural network here, and these are way smaller than the cardinality of states and axes. So some comparisons between POMDP and POMDP-DRL, right? So both of them can tackle observational uncertainty. They're both relying on dynamic programming to take care of the curse of history. They can deal with stationary and non-stationary environment. There is no need for policy reevaluation if at the end, the suggested actions are not followed for any reason. They can, POMDP deals with both finite and infinite horizons. The POMDP, with DRL can tackle both, but with the infinite horizons, we need some specialized handling. There are global optimalities guarantees in this case. Here we lose those direct global optimality guarantees because of the deep learning approximation. But this POMDP, right, is difficult to scale to large system. While with the DRL, right, we can go to hundreds of components in multiple states and action states. Another advantage of the DRL is that we don't, our modeling environment works directly. So we have a finite element model, a fluid dynamics model, database, structural health monitoring data, exactly as we have been doing so far. We can just use this the way we have been using them, right? No specific model is needed. Well, in this case, we need the explicit matrices to be provided. So model uncertainty can be also implemented. In this case, we have distinct alternative models that can deal with that. And here, any way we're updating our models, the same is true for this. So without going into detail, we recently in this paper, right, suggested an architecture, a multi-agent actor critic architecture for this type of problems we have been discussing. So we have the so-called critic network here that gives estimations of this value function V. And we have this actor network that provides us the policy that we have for the whole system. And the key to this was because traditional deep reinforcement learning schemes have problem with the cardinality of actions for the system. So what we did here is we decompose its control unit to have its own actions without losing any generality. And then we have to take care of this in this post-processing step, connecting the two networks together. So this can also work with beliefs, right? Dealing with POMDP problems. And again, the main idea here is also simple, right? We just need to have a way to update the parameters of these networks, right? Based on the data that we're getting. So there are different methods to formulate those gradients, right? And we're explaining in the paper here how we did it. So for the policy gradient for this network, right, relies on the so-called advantage function, which is basically a normalization of the Q function we saw before, right? So if you see the advantage function relies on actions, so we're taking the actions from the actor network for this, and it also relies, right? That's the advantage function. It also relies on the value function. So the value function that is provided from here and the actions that are provided for here are combined to give us the advantage function. And having the advantage function, right, we can then use it, as you see here, for both the gradient of the critic network and the actor network, as we see. So we can also put constraints into this in this paper, which is in print, and again there is an archive version. We're also including constraints. There are two types of constraints that we have included: the state augmentation constraint for deterministic quantities like budget. We cannot exceed a certain quantity, and we also have so we include this as a state into the system. And we also have stochastic cumulative quantities, risk, reliability, any other metric we want that, that is probabilistic, mean values. And we have Lagrange multipliers for this, in the general formulation of constrained optimization. As you see, the Lagrange multipliers are external, right? They're not connected to the neural networks here, but we just have to consider them, in this post-processing part, taking derivatives, including them in the advantage function and all that. So the constrained with the unconstrained versions are very, very similar. Right, in the constrained version, again, we need all these gradients. We have the y, which are the augmented states for the hard constraints. Here we don't, and then we have an extra gradient here for the Lagrange multipliers. So some examples, right? So we have here 10 components, 4 damage state. It's there is non-stationarity in these transitions, and there is a gamma factor of 0.99. We have 4 actions, right? Do nothing, minor repair, major repair, and replace the component. Each of them, the major repair improves both the damage states and the deterioration. So the available number of actions is 10 to the 6. Because we don't have optimality guarantees here, where we need some thresholds to compare against. So here we use some things that are used currently, right, based on condition-based, time-based maintenance and prioritization of components. And we have different observability levels from perfect observations to 70%. So this is the training after a few thousand episodes in this optimization problem, right? We saw that the DCMAC, the protest did well and passed the baselines by 15 to 50% depending on the baseline. But we also were very, very surprised to see that this also happened when the baselines were working under better observability. So this is the DCMAC results, like lower is better, and this is 70% accuracy, 80, 90, and full observation, full accuracy in our observations, right? Still perform better than other baselines that we're working with perfect observations. So this is one realization, but now for the system, same as I showed before. Right, so we have here, four different states for each system, right? The probabilities for, being in each one of them, and we have minor repair, major repair, and replace action for all the components, right? So each agent is acting on its own independently, but they want to optimize they have a collective objective of reducing the lifecycle cost. So solving this model, right? There is a mapping based on the beliefs, right? What's the optimal action to take. So the same problem, but now with constraints, right? One of them is to, right, we have budget constraints, life cycle risk constraints, and also we want, to have access from A to B, right? In this, for example, transportation network. So again, high states and action spaces. We need again to some baselines to compare again, right, based on risk-based, time-based, and so on, and prioritizations. Again, we saw very good results with the DCMAC poll surpassing the best baseline by 42%, and we're also can here quantify the different costs that are needed in the optimal policy, right? Inspection, maintenance, shutdown costs, risk costs, and so on. So we can also see, changing the budget levels, the different life cycle costs, and how the different categories of costs are changing. And we see here, 2 different scenarios. This is the high budget scenario, right? And this is a low budget scenario, and we see lots of control actions here, maintenance actions, lower in general failure probabilities and failures, right? And here less actions for some components, right? And more failure events in general. So we also need to take into a good look into what we're actually getting out of these policies. So this is just something that we investigated. This is again the high budget scenario and the low budget scenario. So we see here for the different 10 components in time, Again, the different maintenance actions to take and the different inspection actions. And of course, according to what budget we have, these are completely different between the two cases. We saw here, for example, right, that the algorithm suggested to inspect component 4, mainly just component 4, and we saw we started to see why that is. And the reason is that type 3 is the worst deterioration rate we have for this component, and this path from A to B that includes component 4 is the most reliable path. Right, so the algorithm here identified the fact that this is a critical component. So in the low budget scenario, go inspect this a lot to be sure that things are okay. So we can do the same thing for risk, right? Changing the risk constraints, we can see how the cost is distributed, the different components of the costs, and we can also see here another realization of this. What you see here highlighted are parts of where the algorithm identified the fact that because we have here this risk constraints, we need to maintain a lot, right? Maintaining a lot causes system shutdowns of links. So it took advantage of exploiting these shutdowns to do opportunistic maintenances for components of the link that were off for a maintenance, right? So even though if they needed it at that time in terms of what's their probability of failure is, right, they reduce the overall cost overall. So and final example, right, is about the bridge. So our system can be, doesn't have to be spatially distributed, right? It can be, a structural system. Then we're maintaining and inspecting the truss elements here, right? So again, this is a corrosion problem. In time, this is a steel bridge, and the costs were related to the central node deflection of this bridge. Right, so we have again minor repair, major repair, replace actions, and inspections of the whole bridge, right? Which makes sense. We wouldn't go and inspect just one truss member. Different again thresholds to check the performance of DRL. So we saw again good results, 5 to 20% surpassing the strategies of condition-based maintenance. And again, that's another realization, all right, based on this is expected section loss for some bars here of the truss, right? We see the uncertainty when we have inspections, the uncertainty increases, or and the actual section loss, right, may reduce or increase based on what the outcome of the inspection is. And then we have minor repair, major repair, and replacement actions for all of these. And again, another realization of this, right? So these are our beliefs now. For all of these beliefs, right, we have a mapping. So for the due to time, I'll pass this, right? So again, we have here, a mapping, right? A mapping of, if we have a belief about our system and its state, right, we can have a suggested action and suggested value cost for the remaining policy. So some ongoing work on this is that we're actually working on an actual large-scale transportation network now. This is in Virginia, close to Virginia Beach. They have a budget of around 1.3 billion for 5 years. We haven't concluded this work yet, right? Based on preliminary results, we see again, around 20 to 30% improvement. So which has to do with considerable amount of money now, based on this network. So some challenges, right? They're the ones we've discussed about computational complexity, right? That it seems that if we combine the two together, right, we can achieve good results. Of course, scaling up is always a goal and a challenge, right? Can we do it for millions of system components, right? With dependencies and for numerous interdependent systems, we're not there yet, right? We need new architecture for this. We need theoretical developments for this. We need, implementations for this, right? The training is also stochastic with this type of models. So, you can train it once and maybe not get, as good results, and then if you train it again, right, you can find way better optimal policy. And the current available platforms as a TensorFlow, this is the one we use in this work, right, with Keras or PyTorch or others, right, are still improving and maturing. So, you know, from version to version now, you may also see differences in their, you know, in their performance. So we need, you know, also mature computational platforms for these things. The other thing I want to mention is about model uncertainty, right? As with, you know, this is an optimization problem, and we rely on models, of course, and data, but also models, right? So as with all computational estimations, model accuracy is important. We can use all type of models, finite elements, or just purely data-based, right? And if we want to update our model as based on incoming data, we don't necessarily need to retrain our policy, right? So if we parameterize it and this is considering the training, right? We can, as data are coming, update our model and keep our policy without needing to rerun it. And something else here, right? This is you know, just some thoughts in future directions, is that so based on incoming data, we're both updating our state and the model, right? And when we update our states, things are more accurate, right? We have better estimations for states than we have for models, and that's what you know, that's an important component. I think will play a role in the future, right? So for example, here you see, for, you know, this is some you know, unscented Kalman filter variants we have been working on. And for certain noise and other things, right, that, you know, they're quite off in terms of the parameters, right? The true is 2. We start from 3 here, right, and, you know, we got 0, right, which is off, very off, right? However, in terms of the states that we're predicting, right, things are not very off, right? So we get a better approximation for states rather than the model updates, and I think that's important, because we rely on the decisions based on the system, on the state beliefs. Something else I want to mention about this is that we can also learn models from data, right? So if we have a number of data and we have, you know, transitions in time, right? We can fit this from data, this type of matrices about you know, the probabilities of going from one state to another state. And we can also rely this based on some hard hazards, right? So in this paper, for example, you know, we saw how we can do this for long-term stochastic transition paths, right? Based on certain intensity measures, right? And different damage severities, how we can, you know, having a bunch of data fit the mathematical model, dependent Markovian models with this. So we also need transparency in decision making. That's an important point, right? Can decisions be autonomous in reality? You know, it depends on the system. But, you know, if we study the POMDP-DRL policies, we learn a lot, right? So they can, even if we don't want to use this, I think this policy can inform decision makers. And they can also guide better threshold-based heuristic approaches, or just, you know, things we have been doing, for example, in terms of, you know, the periods of inspection or other things. It's also important to know that if a suggested action is not followed for any reason, the policy does not need retraining, right? We just attain a new belief and we just start again from there. Human specified actions can be incorporated in the training process, right? So if we want certain things that you know, to be in our final policy, we can embed them into the training process and include them in the final policy. I'm almost done. Constraints due to safety reasons can be incorporated in the training policy also, right? So if we want to be safe for something, we can put constraints, right? So for that, as we saw. And finally, right, we you know, another future work and challenge and you know, something to discuss is, you know, can we use direct you know, the direct use of online structural health monitoring data? Again, this is based on a recent work we've done based on a Kalman filtering variant that is, you know, has to do with unscented Kalman filter, right? Same accuracy, but less computational cost. Right there, we have just accelerometers, right? And we update the states, right? Axial forces, moments, right? Parameters. So, you know, can we embed this directly into our DRL framework, right, in the future, instead of having, you know, other type of data that need lots of processing. So I'm concluding, right? So these are powerful approaches, right? They have shown to solve, you know, quite a few problems that, you know, were even intractable in the past, you know, within and outside engineering. And there is lots of opportunities for further research, development, and implementation, right, in multiple directions. So this research has been funded by National Science Foundation, the U.S. Department of Transportation, and of course Penn State. So I thank them all, and thank you also again for the opportunity and the discussion. Looking forward to the discussion whether we can actually train intelligent engineering systems like in this way. Thanks a lot.
Thanks. Sorry, thanks, Kostas. Thanks, Jannie, very much for these insightful and inspiring presentations. And I guess they also inspire a lot of questions and comments. So far in the Q&A, I don't see many questions. So feel free to write there.
Maybe we could start from the one that is there, because it could link to both talks. Actually, this one is for Jannie, and it's asking, what if instead of using equidistant inspection data, we rely on continuous monitoring? So therefore, a continuous stream of information. And I think Kostas also mentioned the potential to incorporate this. So, but the question is, how beneficial would it be to get this continuous information that really relates to structural health monitoring into account?
Well, it was actually also what I studied here and took into account, and what we could see is that it really depends on how you use it for decision making. So you can use it in a wrong way where you don't do optimal decisions, and then you'll actually end up worse than if you do just equidistant inspections. And also if it ends up resulting in a lot of false alarms where you do inspections that would else be unnecessary, then and also depending on the cost of the monitoring system. But in the study analysis that I made, it seemed that there definitely could be an improvement and decreasing in costs. But again, depending on how reliable it actually performs.
Yes, and you also showed the reliability of the monitoring system in one of the slides, if I remember it right. How do you calculate this probability of detection, or correct detection, was it the term, let's say?
Well, this was based on, so there was this this testing made, so there was like the test or the training data first, and then based on these
so with labeled data
so it was with labeled data exactly.
Mm-hmm. So which is then important maybe to have as well for these kinds of analysis of the reliability of the system.
Yeah, because the problem is that when you actually then install a monitoring system on an operating wind turbine, and you get other types of crack than this leading edge spall in this specific location, then how will that affect the response? You don't really know that before. So, well, we probably need someone to take the chance and install these monitoring systems and on a wind farm, so that we'll get the data, and then we'll see afterwards if it was actually beneficial.
Mm-hmm. You're right. Yeah.
Yes, so maybe this also leads over a bit to I think what both of you mentioned some part in your presentations, is that, I mean, particularly also Kostas showed really how, there's a lot of potential in, and we have really already, we can do a lot of great optimization, but on the one hand, but on the other hand, we're still really are very sparse with real world data. And so we can train these algorithms with data that we create from models, but these models are often highly idealized still, and not based on a lot of real world data. And I mean, Jannie, you showed some examples where you have real world inspection data, and I know that this is very difficult to get in real life because the operators don't want to make this public, maybe understandably, and even for research purposes, it's often very difficult to get. And often it's not even, at least up to now, not even collected systematically. by these large operators.
Yeah,
So
definitely.
your
And this
perspectives.
and this ownership of the different types of data that are all relevant to use in the model. So it might not belong to the same. So you might have some of the data belongs to the wind turbine manufacturer, and some of the data belongs to the owner. So it's quite difficult if you then want to actually use all of it.
Right, and that's exactly right, and also Jannie mentioned very nicely in her talk, right? And so these games, these arcade games, they have the environment is perfect, you know, that's it, you know, these are the rules, this is how you play it, you know, everything's perfect. In our case, we cannot do this, learn just based on actual data, right? Because of the wind turbine is destroyed, and you know, that's not a good outcome. So however, I think, you know, so these are the, you know, the bad news. The good news, I think, is that we don't know the future anyways, right? So we're trying to optimize. We're trying to optimize based on what we know now. So yes, we can also be biased data or uncertain data, right? You know, in any case, we're trying to find, you know, do our best based on what we know now, and, you know, update our knowledge as we go on. And the problem with this is that we cannot do, you know, I can't think of a way to actually, you know, do this otherwise, because also, as Jannie mentioned, right, we need an alternative world, right, where we actually, you know, in real life, we try different outcomes, and we collect different data, and then based on those we learn. So I think the best, or, you know, in my opinion, the best we can do is to guarantee safety, right? To guarantee safety based on our policies, and then you know, if we learn and try to optimize as much as possible, right? To gain efficiency, and then as we go on, if we'll know more based on data, then even better, we can perhaps, you know, potentially improve our decisions.
Since you mentioned learning from data, and since Mike, actually, you could unmute yourself and ask a question. I see you noted something relevant, which of course is true, the usefulness of historical data, which was also mentioned actually for inferring maybe the gradation models, I think, right?
Yeah, thanks, Eleni. Yeah, sorry, I didn't know if I should speak or not.
No, go ahead.
Yeah, no, first of all, excellent presentations to both our speakers. It was a real pleasure. Yeah, I just wanted to comment that in the cases, maybe this is true of the wind turbines, Jannie, I wasn't sure, but when you do have lots of historical data, inspection data, even if it's just human inspection data, we were talking about in some papers about how that can be mapped to the kinds of transition matrices that Kostas spoke about, you know, to get probability transition matrices that can then be used to inform a probably biased, but nonetheless a prior on a degradation model. You can actually set up a historical record of what degradation is, unless your inspection data is 100% uncorrelated to reality, which is not typically the case. So.
Yeah, I totally agree. The issue is that, well, often these historical inspection data, it's like if you only have one inspection for each wind turbine blade, and you then the only other information you have is like the age of the wind turbine, which might not even be the same as the age of the blade, then there can be a lot of, you can calculate transition matrices from that, but there are definitely some uncertainties associated with it.
You're absolutely right. And the first thing we learned in our mapping of miter gate inspection data to these transition matrices is that inspectors are horribly biased, and you have to take that in and detrend that. They tend to want to rank everything at a relatively high inspection rate until it's basically already failed, and to avoid work. It's interesting, but anyway, excellent presentation, both of you. Thank you.
Thank you, Michael, and also to add something on this, that, you know, something else that we see that is that's a problem with actual historic data, for example, for transportation networks, is that things are getting maintained, and So you can't find, a large period of time that, multiple years that you need to see, the deterioration trends. And sometimes also, at least for transportation networks, right? These maintenance actions are not well documented. So suddenly you see an improvement, and you don't know, is this noise? Is this because of bad observation? There was a maintenance happened here, or, what is it?
I think Adonis would like to ask a question.
Yeah, thank you both for the presentations. I have a question to Kostas, regarding one of the last slides. You showed that having a uncertain Kalman filter on some variance of it, you can get a good estimates of the state. And you mentioned that it is more important than model updating. And however, if you have a good state estimate and a bad model, this leads to bad predictions because you cannot predict well in the future. And did you mean that it is more important within the POMDP plus reinforcement learning framework, where you need the state to move on to the next decision? Or
exactly as mentioned. So that when you make, as you mentioned, right, the parameters have to do with the future predictions, right, and the states with where you're currently now. So in the partial observable Markov decision process, POMDP's framework, your decisions are relying on the current posterior distribution of the states, right? So even if your model is off, right, as you said, your future predictions, right, the transitions you'll get will be off, right? But you will, that's a problem if you take decisions without inspecting or observing, right? But if you observe, then the states get updated, and this is when you actually, the posterior belief is the one you're relying on. So it may be possible, right, that the solution you get at the end suggests to do that, to maintain without inspecting, right, in some cases. So and this is where I see where I mentioned, if the decision maker is not comfortable with this, and may not well be, right, regardless of whether this is deemed optimal in the way, for based on the model we use and the policy we computed, right, you can embed these things, this decision maker preferences, right, into the training, right, and say, look, I will never make any maintenance acts without the same time inspecting first.
Yes, so we have also some questions still from the audience, and the first one maybe to Jannie was the question about the dependent observations, because you talked about that, and also the challenge maybe in assessing that correctly. And the question is what factors actually lead to dependent observations?
Well, that can be, basically anything that will introduce some time-dependent uncertainties. So I think if you look at the inspections that are made once a year by a different inspector, there will not be, they will be, quite uncorrelated and independent. But if you have a monitoring system, there might be some variables that are actually affecting the outcome. It can be both related to the system itself. It could be some environmental parameters that you don't know that you should account for. It could be taking the example with the wind turbine blades, then the location of the cracks. So that could affect this relation between this expected value of the monitoring and this damage size. So if we have a damage in some location, then it will affect this expected value of the monitoring outcome in a given way. And even if you have a lot of observations, they are not like independent draws from the full distribution. It is conditional on this parameter. That could be dependent on the location or many other things.
Maybe a further question, which seems to be posed and probably is indeed a challenging one, is how to incorporate data with different levels of uncertainty. I think partially already there was a hint about that, meaning either lower resolution tools for evaluation or higher resolution tools. But what I consider even more challenging is the second aspect of that question, which refers to different parts of a bigger system, so a global structure with components, which though receive different levels of inspection, because possibly some components are more critical than others, are more routinely inspected, and others are hard to reach, and possibly inspected in rarer intervals or not at all. So how would you treat such an assembly of components that has to be decided upon?
Yeah, I can start. Well, I mean, you can in this framework you can include this because the number of components you have, it's not necessarily the control units you have, right? So meaning you can bundle things together if an action has to do with all of these units or not. Right. So if, for example, you do for the foundations of the wind turbines, you do a specific monitoring technique, right? You can include this for all of the parts of the system. And then if you're doing specialized inspections for the upper part of the turbines, right, then you have that part as a different action to take for the different components. So it can be implemented. Right, for example, in the case of the steel bridge I showed, right, we had the whole structure being inspected at once, right, since we usually inspect all of the truss members there. But for the different examples, right, each bridge and its component has its own actions, right, that we can also select the inspection accuracy. Now, in terms of how someone, if we want to define the inspection or observation or monitoring accuracy directly from data, that's a question to be seen. I mean, sometimes you do have completely different monitoring systems, right? And one is more reliable and more accurate than others, right? But some other times that's not obvious, right?
I think what is non-trivial maybe is to characterize all of this in one indicator that is the indicator on the basis of which you, let's say, function, the state of your system, and whether it's decided as a weighted metric of the components or each component has its own indicator.
Yeah, so the state of the system, again, doesn't have to be one variable, right? So it can be anything. It can be accelerations and crack sizes and displacements, and so all of them can define the state.
No, this is true, but then you have different components defined sometimes by strain, others by acceleration. So therefore different thresholds and different methods.
Right.
In that sense, it is a bit more complex than maybe the examples, but I think it is possible to incorporate it in the framework. Yeah.
Yes. Actually, it is also possible to, if you have a set of kind of imperfect inspections with at least different type of imperfect inspections, it is possible to use the redundancy to kind of infer the quality to some degree, if they are not too correlated. We did something like this for sensors in autonomous cars that seems to work. It is not perfect, but you can learn something from that as well. But I was wondering, Kostas, actually, you mentioned that there is no need, so if you have new data, there's no need to retrain your policy. And I guess there's no need to retrain your policy, but wouldn't you get better results if you do retrain your policy, particularly if you have observations that do not really correspond well with what you had initially assumed?
Yeah, so this is what I had in mind with this is the following, that if you, in your training, take into account the fact that you have a parametric model and this gets updated, right? So basically then what you're also having a posterior distribution on top of those parameters. So you're making, you're fitting your neural networks, right, to these value functions that also include these parameters. So if according to if the training is okay, is good, right, and because that's interpolation, right? If you extrapolate, this doesn't work. right? So if you take into account, right, the different parameter posterior distributions that you can have, right, then you have already taken this into account. Now, as you go on, right, if you see that that in most cases will rely on a fusion of different parameters, right? They have some probability of being in this range and some probability of being in this range, and this is how you you basically train your model, right? So if you go on and you see you have strong preference for a certain set of parameters, right? You're very close to one for a certain set of parameters with your data, and of course, right, it may be worth retraining the model based on that, right? Because you'll have more accuracy in this case, but it's not needed in the sense that if I have a model updating, that every observation I take, I need to retrain because I updated my model, right? If we see that we have a trend here, as we have a bias that we haven't considered, right? Then it's good to retrain.
Yeah, okay, yeah, that makes sense. Good. Let's see. We seem to have answered all the questions, but
maybe a question to Kostas for that last part that you showed, which was on online estimation and the use of Bayesian filters. And I think Antonis already sort of asked there. You show a good state estimation, but I imagine it would be useful for you to also have a good estimate of the variance because it quantifies the belief in your state. But we know from these filters that this really depends on the selection of the noise parameters. After many steps of the estimation, it sort of converges to some sort of limit that is just a function of these assumptions on the noise parameters. And it's not always a very good way, let's say, to do the estimation. Do you think there we can have improvements? Is it nonetheless a useful estimate, the variance that comes from these filters?
So I think in general that this field of connecting this type of health monitoring data, right, through filtering or other techniques with this type of optimization approaches, I think it's a very personally, I think it's a very promising field for future, right? And it's lots of work. There haven't been things that have been done there, and it's an even larger problem of what you mentioned, which is the following: if someone uses POMDPs, right, you need to update your uncertainty, right? So you need to propagate your uncertainty and update your uncertainty. So that's a problem again of general uncertainty propagation and uncertainty updating of probability density functions or probability mass functions. So as you mentioned, right, I mean, ideally, and I know you and Adonis and have done work on this, and I think Diane was also more, right? I mean, you can use particle filters, right? And then with particle filters, theoretically, you can track the whole distribution, which is this is actually what you need, right? Because based on these particles, you have an estimation of your posterior, and that's what you need for this type of applications, right? So, and then as you mentioned, right, after many observations, things start to not work well.
Yeah.
But the good thing about that is that not about not working well, but the good thing about this type of approaches is that they basically break the problem, right, into different components that are long, that are open problems in engineering, right? So one component is stochastic models, right, and reliability updating, right, whatever we are using so far, right? The other is, updating of probabilities and propagation of uncertainty, right, in continuous or discrete spaces, right? And the third component is optimization, right? So these three can, there are challenges to combine all of them, but there are also, the challenges that have to do with the first two, right, are based on things that, as an engineering and stochastic community or engineering community we have been using. So in other words, to make this shorter, is that you can, you can use anything you are already using and combine it with this optimization.
Yes, I suspect it could affect the outcome, but nonetheless, it's still an interesting or a useful framework to follow.
Maybe if I can have a final question, maybe to both of you, but maybe specifically also to Jannie, because you work a lot with wind farm operators, and also not surprisingly in Denmark. And so you're in contact with this, and you have worked both with these kind of more heuristic approaches that you presented, but you've also worked a bit with POMDP. And how, I mean, as Kostas showed, no, ultimately we can get better policies in the sense of okay, lower expected costs when we use these algorithms. But how likely do you think it is, or how easy it is for operators to actually accept that now and maybe also in the future? No? When is the point when they will actually, in practice, accept something like that?
Yeah, thank you for that question, because it's actually, I think that there's a transition going on at the moment where they are really starting to see the light in this kind of methods, and where there are actually more and more who learn about these approaches and wants to apply them also. So they, I think that but of course it's important that they trust whatever system it is, and somehow qualitatively understands what's going on in some way. But I think that within a relatively few number of years, we will see that it will really change in this in the amount or how much these methods will actually be applied in this industry.
Yeah, I mean, I actually my personal experience is that at the higher levels, or the top management level, it's actually very good to come up with these fancy sounding. But I mean, of course, these are very nice techniques, but they also sound fancy. And at the say top level, my experience is that you reach them, but whereas at the engineering level, my experience here is that with the people that I work with, which is maybe a bit less advanced than in your area, is that there is still a lot of skepticism and also, I mean, it's really practical difficulties because it's hard to understand. It's a black box for these engineers, and so they have a certain reluctance to accept that, and there's also a certain fear of at some point maybe to be replaced by a machine. And this, I think, not. I don't know. Maybe you should ask Kostas when will we be all replaced by a machine? But
yeah, I'm optimistic. We'll see.
And we are replaced, and we can just go to the
no, that will be adopted. My experience is that unfortunately is case by case based on who is handling the maintenance. Right, I mean, you can have a network of bridges in 2 different states and or 2 different counties here, right? And one is more like willing to try, right? And it's you see that they're more interested, and others like no, we don't want to touch what we already have currently. So I think it's important to see I mean, if we can actually gain advantages, because that's an optimization, and you try to optimize an objective function, right? If you find better optimum, then I think the question is, can we do it safely, right? And maybe that safe part is where some interventions are needed, right, in the problem, like either in the constraints, or if someone, as I said, is not comfortable with certain decisions, right? Don't follow them. And it's even better if you put that into the training, so you can have like a mixed approach of I necessarily want to have this type of decisions and actions being taken, but for the rest I don't mind whatever the algorithm suggests. So hopefully this is a way forward. We'll see. But yeah, I mean, I'm optimistic for long, for the future.
That's a nice punchline. Maybe we ask Jannie to do the same. So what would you like to leave us with before we close?
Well, going in the same direction, I think that we're really seeing that they are becoming more open also for these probabilistic methods, because, well, it's when they don't like being stuck in these old like schedules. When they come with some better methods for inspections and so on, then they don't really get the credit unless they also have some method for assessment that can consider this. So this is where these methods also come in and can offer to take all this better information into consideration. I think this is something we'll see, definitely.
Thank you both.
I guess that's it, but it was really great. I learned a lot again, and I think it was very inspiring. And yeah, thanks to both of you for participating.
Thank you very much for the opportunity again and the initiative, for this whole series. It's
we hope to have you join also in the next sessions and join the discussion as well.
Yeah, absolutely.
Yeah, thanks a lot for organizing this and inviting us to do this talk.
Thank you both. Yeah, go ahead.
Sorry. Well, maybe that just brings us to say that the next session will be on June 10, so on Thursday again, and that will be at 5 o'clock.
Mm-hmm.
And it will be Professor Faber again from Aalborg and Professor Pozzi from Pennsylvania as well. So we stay in the same geographic regions, but I believe quite different angles on the same topic. Great. Looking forward to seeing everybody again, and yeah, stay safe.
Thank you. Have a nice day, everyone.